Hi everyone, in this video we look at how to perform transformations of trigonometric functions. So here we're told if a function is written in the form y is equal to f of k times x minus d plus c, the following transformations can be applied to the parent function f of x. This is something that we looked at in previous units. Now we looked at how mapping rule can be used to transform key points on the parent function, and you can absolutely do that in this section as well. But in this video, we're going to look at how to just look at the key properties of trig functions and graph according to those key properties. So recall that the absolute value, if an equation is written in the form y is equal to a times f of kx minus d plus c, the absolute value of a causes a vertical dilation by a factor of a. If a is between, or if the absolute value of a is greater than 1, this is a stretch by a factor of a. If the absolute value of a is less than 1, this is a vertical this is a compression, vertical compression by a factor of a. Here I've graphed y is equal to sine of x, and let's think about what happens to if we graph y is equal to let's think about 2 sine of x, and let's think about what parameter of a trigonometric function this varies. If I perform a vertical stretch, well, this point would be 2. We'd have this point would stretch down to -2, and our graph would look something like this. And here I've only graphed one cycle of y is equal to sine of x, and I'm only graphing one cycle of y is equal to 2 sine of x. We could graph more cycles than that. And if we look at what happened to this, the function y is equal to 2 sine of x, we performed a stretch by a vertical stretch by a factor of 2. This increased the amplitude by a factor of 2. So the absolute value of a is the amplitude. So the absolute value of a is the amplitude. That's a really important thing to note. Now let's see what happens if we graph y is equal to, if we graph y is equal to 1/2 sine of x. If we graph y is equal to 1/2 sine of x, we would have a point here, a point here, a point here, a point here, and a point here. So this would be a vertical compression by a factor of 1/2, and again, this is a again is the amplitude, or the absolute value of a again is the amplitude. We can examine what effect a being negative has, and we looked at in previous sections that if a is negative, like let's suppose we have y is equal to -1/2 sine of x. Well, this would just be a reflection about the x-axis of y is equal to 1/2 sine of x. So we would have a point here, a point here, a point here, and a point here, and a point here. So our graph would look like this. And that's, again, just one cycle. So the amplitude is still 1/2, but we just have a reflection in the x-axis, or about the x-axis. Okay, so we've examined now what the parameter a does on the parent function of f of x, or on a sinusoidal function. We've determined that the absolute value of a is the amplitude. Now let's look at what k does. So we've already, in previous units, we looked at the fact that k is a horizontal dilation by a factor of 1 over the absolute value of k. If k is negative, there's a reflection in the y-axis. So let's see here. Let me just clear some of this. If we have, say, y is equal to sine of 2x, well, this we know that this is a horizontal compression by or a horizontal dilation rather by a factor of 1/2. So it's going to compress the graph. So instead of this point being here, we're going to have a point here. This point is going to be here. This point will be right here, and this point will be here. Oh, sorry, never mind. This point would be here, and 360 would now be at 180. So our graph is going to look like this, and that's what one cycle of y is equal to sine of 2x would look like. So notice that the period was instead of the period being 360 degrees, the period is now 180 degrees. So we divided the period we divided the period by 2. If I had, if I wanted to graph y is equal to sine of 1/2 x, well, this y is equal to sine of 1/2 x is a horizontal stretch by a factor of 2 of y is equal to sine of x. So this graph is going to look like this. We'll have a point here. Instead of this point being at 90, this point's now going to be at 180 degrees. Instead of this point being at 360 degrees, this point is now at 720 degrees, which is going to be over here. So we've got a point here. Instead of this point being at 180, it's now at 360. Instead of this point being at 270, it is now going to be down here. And our graph would look something like this. So what you can see is that when we apply this horizontal stretch, this doubles our period. And if you saw the relationship between period and the k coefficient, the period is going to be equivalent to 360 degrees divided by k. In both these cases, you can see that for y is equal to sine of 2x, that the period was 360 divided by 2, which is 180 degrees. For y is equal to sine of 1/2 x, the period would be 360 degrees divided by 1/2, which is 720 degrees. So as a rule of thumb, or as a rule, I guess, the period is 360 degrees divided by k. Now let's look at horizontal shifts next, or what this parameter d does. The parameter d represents a horizontal shift to the left if d is greater than 0. Oh, sorry, this should be this should say to the right if d is greater than 0. So let me correct this. It should be to the right if d is greater than 0, or to the left if d is less than 0. So what that means is that if I have y is equal to sine of x plus 180 degrees, this is a horizontal shift to the left by 180 degrees. Y is equal to the sine of x minus 180 degrees would be a horizontal shift to the right by 180 degrees. So that just shifts the graph either to the left, like in this example, or to the right, like in this example. We also call horizontal shifts, when we're dealing with trig functions, we call them phase shifts. So the horizontal shifts are called phase shifts for trig functions. And if the phase shift is to the left, that would be phase shift by a negative phase shift. So like in this example, we would have a phase shift of negative 180 degrees. In the example below, this would be a phase shift to the, or a phase shift of positive 180 degrees. So phase shifts to the right are positive, phase shifts to the left are negative. Next, this parameter c causes a vertical shift up if c is positive, or down if c is negative, and it's always by c units. If we think about what this does to the equation of the axis is just y is equal to c, because the equation of the axis is normally y is equal to 0. If this is a shift up c units, then the equation of the axis would just be y is equal to c, and same thing if the equation, or if the shift was, if c was negative, this would be a shift downward c units. So the equation of the axis would still be y is equal to c. So let's go through and let's look at an example where we have to apply a bunch of different parameters, or a bunch of different transformations to a sinusoidal function. So in problem 1, we're told to graph the function y is equal to negative 2 sine of 2x plus 180 degrees minus 1 on the grid below. Now, the first thing to note is that this is not written in the form that we have above. Because in the form that we have written above, k, this k value here, is factored. And in the example that I've given you, k is not factored. So that's the first thing that I'm going to do. I have to factor out k. So I've got y is equal to negative 2 sine of 2 times x plus 180 degrees minus 1. And I'm going to rewrite this as minus 2 sine of 2 times x plus 90 degrees minus 1. So now we can, now that this is in factored form, we can look at all the different parameters that we have. We have that our value of a is equal to negative 2. So our amplitude, which is the absolute value of a, is just going to be 2. Here we have to perform a reflection about the x-axis and a vertical stretch, since the amplitude is 2. Our period, if we think about this, we have a horizontal compression by a factor of 2, or by a factor of a half. So our period is going to be, the period is going to be equal to 360 degrees divided by 2, which is 180 degrees. The phase shift, we have a shift to the left by 90 degrees, because d is equal to negative 90 degrees. So this is a phase shift of minus 90 degrees, or a shift to the left of by 90 degrees. The equation of the axis is just y is equal to c, and here c is equal to negative 1. So the equation of the axis is y is equal to negative 1. So now that we've written down these 4 parameters, and maybe we'll just make a note that there's a reflection about the x-axis. Now that we have these 4 parameters, we can go ahead and graph our function. So I always start by graphing the equation of the axis, and let's think about what scale we're going to want here. Here we can say that this is, that we have 1 unit, and this is going to be negative 1. This would be 2, 3, and 4. And if this was negative 1, this would be minus 2. This would be minus 3 and negative 4. So the equation of the axis is y is equal to -1. So that means we're going to this horizontal line is going to cut our periodic function in half. So I start by sketching that line. The next thing I'm going to do is let's look at the amplitude. Our amplitude is 2, so that means we're going to have a maximum value of 1 and a minimum value of -3. Okay. We also know that our period is 180 degrees, so that lets us determine what scale we want. And here, let's try to graph. Let's sketch 2 cycles of this function. So the next thing that I have to do is I have to figure out what an appropriate what an appropriate scale is for my x-axis. Since I want to sketch out, since I want to sketch out 2 cycles, I'm going to need at least 360 degrees on my horizontal axis. So let's say that this is 45 degrees. This would be 90 degrees. This would be 180 degrees. This would be -90 degrees. And this would be -180 degrees. Okay, so normally the graph of sine of x would look something like this. We'd start at the origin, but here we have a phase shift to the left, or we have a horizontal shift to the left by 90 degrees, a phase shift of -90 degrees. So the origin, let's think about where the origin maps to. The origin shifts down 1 unit and to the left 90 degrees. So we're going to have a point here. Our period is 180 degrees. So 1 complete cycle is going to finish after, if we start at -90 degrees, 1 complete cycle is going to finish at 90 degrees. So we have another point here. Now, I always say to graph 1 complete cycle, think about breaking the graph up into quarters. So a quarter of the cycle, after a quarter of the cycle, we're going to reach a maximum normally for y is equal to sine of x. But since we have a reflection about the equation of the axis, or a reflection about the x-axis, we're going to have a minimum after the first quarter. Now, a quarter of 180 degrees is 45 degrees. So we're going to have a minimum after 45 degrees. And the minimum is -3 degrees. So we'll have a minimum here. We'll cross the equation of the axis in the next quarter, or after the next quarter of the cycle. And then we'll reach a maximum after the next quarter of the cycle. So we'll have a single cycle look something like this. So that's 1 cycle. After I have graphed the first cycle, I can just graph another cycle by just continuing this pattern. So I would have a maximum here. I'd cross the equation of the axis here. I would have a minimum here, and then I would complete 1 cycle here. So another cycle looks like this. I can do a better job sketching that. So there you have it. There's 2 complete cycles of the graph of y is equal to -2 sine of 2x plus 180 degrees minus 1. So again, what we did is we broke 1 cycle of the graph of y is equal to -2 sine of 2x plus 180 minus 1 up into quarters. and then we kind of sketched each quarter of the cycle. We'll look at another example in the next video of graphing sinusoidal functions, and we'll also look at how to come up with the equation if we're given the graph of a sinusoidal function.